All right. Any questions before we get going? Not about the assignment. Nothing. So last time we were learning about while loops, right? Can we see this just fine, or was it better with the lights off? It's fine? Yeah. Okay. Yeah, we were talking about the loops, and we had this funny little thing here, which I think was calculating factorial, right? Now, a couple people knew what factorial was, some people didn't, but whatever. I'd also like to point out that the way this function computes factorial is a little, I don't know, if I were to actually really want to run it or code this, I would do it a completely different way. But it does what it does, and the exercise was kind of figuring out what it does. So, I mean, we kind of did this when talking about, we were kind of talking about this idea when we were considering functions. But encapsulation, which is a fancy word that doesn't mean anything overly complex, we write a little bit of code, and you probably, like, the assignment made the functions for you, like it told you what you got to do. But, you know, let's say you're writing your own code to solve a problem. Like, on a given day, maybe I'm writing some code to do some sort of analysis of something, I don't know. But it's not going to be like just like a couple lines of code. It requires a little bit of coding. I know I sound like a broken record, but no one sits down and just starts coding. That doesn't happen. They'll code a little bit, hit run, make sure it works. Code a little bit more, hit run, make sure it all works. Maybe there was a mistake, I gotta go back and fix it, run, okay, now it works. And then I start to think, you know, what I've written so far kind of like groups together logically. Now what that means is kind of like, you kind of get a sense of this through experience, but maybe I wrote all this code to do some sort of input, right? And all the code dealing with input kind of makes sense to be together, and I know it works, so I'm going to put that code that I wrote inside a function called like get input. And then I continue writing the code I need, and I could just call the function get input now. And I write a little bit more code, and then maybe I think of a new function I can encapsulate some amount of ideas into. Using functions is amazing because, you know, it makes it easier to write code. It also helps us group things logically. It also helps us keep our code kind of well organized. We're going to go even further about how to organize our code and whatnot near the end of the semester. But this strategy of doing a little bit, writing a little bit of code, creating a function, carrying on. Maybe you write another function that calls that function. I don't know. But that is typical. So here, let's do a quick little example. Now this is a non sequitur. There's no non sequitur. Let's do a quick little example. Before any of this, I want to clarify something. We're going to learn about like a numerical method for approximating something. Every year people think like, oh, I got to learn numerical method. No, we're using this idea from numerical methods to play around with this idea of the looping and running until some condition. Don't worry about like, oh, how did the function, don't worry about that. We're just going to play around, and we're going to do this one together, I think. So I want to find out when does cos x equal x3. And that's like mathematical, so when I say equals, I don't mean assignment. I mean that it's kind of like equals, right? When is that true? What value of x is that true? Okay. How are we going to do this? Now, who here has extensive experience with numerical methods? No, you don't. So here's what we're going to do. This right here, if we compute this, if we pick some arbitrary value of x between 0 and 1, and I plug it into this little formula here, what this will kind of do is give us an approximation of that when does cos x equals x cubed. It'll give us an approximation, but it won't be very good. But what we can then do is take that approximation and run it again through that x minus cos x minus x cubed divided by negative sine x minus 3x cubed, r squared. I can keep running that over and over. I pick a value between 0 and 1. I give it to that little calculation. That calculation runs. It gives me back an x. It's an approximation. It's closer, hopefully, than what it was before. I take that new value, plug it right back into that little expression. It gives me back a new x. That's hopefully a little closer. And I keep doing this over and over and over again. So let's do a quick little example. So here, first I'm going to write this out. So we can get rid of this, I suppose. I'm going to write it as like a function that I can call. So it's going to be return x minus, now I'm going to be doing a lot on one line of code, cos x minus 3x cubed. So, you know what, I need math, so import math. So math dot cos of x minus x cubed, right? And then all of that divided by -1 times math dot sine of x minus 3 times x to the power of 2. That should be it. By the way, if you ever write something like this, I know we know what it means in math notation, but if you forget to put your star there, it's going to be really mad at you. It's going to say, like, I don't know, I can't do that. So you got to make sure we say times. So, run the print. Okay, let's get new x. I don't know. Equals the func time. And what value between 0 and 1? Someone give me some number between 0 and 1. Did someone just say 3 something? Because that's not okay. 0.5? Pardon?
I'm sorry, 0.5?
0.5? Sure, good enough. And then print new x. Oops, what did I do wrong? Oh, it's not print. Okay, well all right, that's interesting. You know what I can do is I can say, like, you know what if I do this? Right? So what I'll do is I'll take the current value of new x, run the function, assign it to new x, and then print it out. And I can just keep hitting run, and it'll keep like updating. If you're scratching your head like, wait, why will that work? It's because new x is currently 1.11214, right? So when I call the func new x, it does all the calculations and then immediately overwrites new x. But that's kind of what we want. We don't care about what the old value was. So we got 0.86547. 86547, okay, I wonder how much it's changing. 8654740. Oh man. It looks like it's converged pretty well, actually. That looks pretty good. So you know what I'm going to do? Let's go to Google. When does cos of x equal x to the power of 3? Let's see if we can find an answer somewhere. Okay, well, this is not what I want. Let's go to Wolfram Alpha, because that should do it for us. Look at that. Roughly 0.865474. And what do we have? 865,474. Wow! We just approximated it without doing any fancy calculus. We just ran the same thing over and over because I hate calculus. Isn't that wonderful? Cool, right? Let's try it again, but let's start with a different starting number. Someone yell out a number. 0.3. Just 0.3? All right, let's see what happens. So we jump up there, and now I'm going to replace this again. New x. It looks like yeah, there we go. We made it. Great. Now, you know what sucks about the process I just did, though? Is I had to stand there and hit run, 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 run until I saw that those numbers were like not changing anymore. When those numbers kind of get fixed, we like to call that like convergence. So we kind of like converge on this number and then it doesn't move anymore, right? But I had to hit run. Whether I had to hit run 3 times, 7 times, or 14 times, I don't know. Let's see what happens if I start with a number like 3.3. Let's just see, just for fun. 2, okay, then we'll change this back to new x. Looks pretty good. There we go, we're in great shape. So maybe it takes a little bit longer, but whatever. So I had to keep hitting run. And I guess it's not that big of a deal. I sit there, hit run a bunch. But imagine I had to do this for a bunch of different numbers on a bunch of different approximations. I'm not going to stand there and hit run for some number of times for each of the numbers I want to do a calculation on. That's really annoying. I want to automate this process. We should be thinking of this, we're programming, we should be able to automate something like this, right? Based on what I was doing, what tool have we seen so far that you think might be helpful for automating this process? A loop. That's not earth-shattering, right? Given the context of what we're learning right now, it makes a lot of sense. So how can we make use of a loop here? So, in the past, okay, we were using while loops. And while loops run while some condition is true. Before, when we were using the while loop, it was like the condition was just some counter check, right? Well, the counter was less than 10, right? That's it. But in this case, we're not going to want to counter. We don't even know what the count is. We don't know how many times we have to hit run. Something else needs to be the condition. What do we think the condition should be? I mean, I was already talking about it, but it's weird to go, it's not weird. Part of the art of computer science and programming is knowing how to go from like the English articulation of what we want to do to the like code articulation of what we want to do. So what's the condition? What do I loop? I keep looping until what? Someone's got to know.
The last number doesn't change.
Until, like that number doesn't change, exactly. So this is tricky. And I'm not expecting anyone in here to really, I'm going to go through this and write the code. And we'll see it together. And there might be some people in here that when I write it, they would have been like, oh yeah, I knew that. But it's fine if you don't, because this is a little tricky. But this type of coding is common. So this is the first time you'll see it. So I want to get, let's start with like x equals 0.5, right? That was a good starting point. So new x is equal to the and then I guess print new x. So this is effectively what I had moments ago, except I just redefined x before. But I need to have it. So while something, I want this to keep running. Okay, what if I do something like do we see the pickle we're in? I want to check, like, how do I keep track? here's the thing. If I want to keep track of what I calculate the new x, I need to also keep track of what x was before, right? Right? So I know, is the before and current the same? So we need another variable. So how am I going to code this? Let's see. What if I do like old x? And then, okay. I'm just trying things right now. This is the best way to think of, to go about this type of stuff. Like, you know what you want to do, but how do we put this together? So we start with that. And what if I make this like x? And I guess here this should be old x. But this, this still won't work, because every single time this runs, it's going to redefine old x as 0.5, right? So that's no good. Because we don't want it to be 0.5 every time it runs. What do we want x to, what do we want old x to become? So imagine this loop runs. Well, some condition, I don't know. Old x becomes 0.5, new x becomes, I guess in this case it would be like 1.1, right? We print it out. Then we go back to the loop because their numbers aren't the same. What do we want old x to become? We can't reset it to 0.5. That's like going back to step 1. Where is the value we care about now? What is the loop ran once. Now it's got to run again. What was the old x now? What does the old x become? Who said what? Why? Exactly. So I'm going to finish writing this code, and then we'll kind of write it out to see what's going on. So how are we going to do this? You know what? I could do this. Let's start with new x is 0.5, just because. And we're going to run while old x is not equal to new x. Then do this calculation. Oh, what did I do wrong? Old x is not defined. Oh, I guess old x has to be we got to start with old x having a value. No, 0. Look at that. And it ran to there. Now, we got lucky here, because remember I was complaining before about floating point numbers being equal? And how, that's risky business, because what if they don't kind of come out nicely? Well, we could do something like this. If the difference between the two, you want the absolute difference, is less than 0.00005, I don't know. There. I guess, oh, well, it's greater than that. There, yeah. So while the difference is bigger than this tiny amount, keep going. When the difference is less than that tiny amount, that's when we stop. So if you're scratching your head a little bit about, well, what's on with this old x being set to the new x, and then we're redefining resetting the new x, as always, you're thinking too hard. Slow it down. And what I like to do when slowing things down is to draw it out. Does this work? Oh, nice. I start, what do I say? New x, or I start old x. I'll just do n and O because I'm super lazy. Okay? Old is 0. New starts at 0.5. Great. I set old x to new x. Okay, so this becomes 0.5. I do the calculation, and new x becomes, let me grab the eraser. What was it, 1.2? 1.1121. I'm not going to go that crazy. 1.1121. Okay? And then we print out new x. Great. We ask the question, is the difference still greater than that little threshold? Of course it is. This and this are much more than 0.00005 apart. So we're going to run again. And immediately, old x gets set to 1.1121. We recalculate this. Why? Because that's what the code says on line 5. And it became 0.90967. We check, are they the same-ish? No. So see how, like, old is what new just was. We keep, old is, what was the last value? New is, maybe I should have called new like current x. Or something, right? But I need to know this one and the one right before to know if the difference is meaningful. Right? Any questions about this? The quietness in the room, that I can't tell the difference between the quietness is like, yeah, I get it. Or I have no idea what's going on. So, questions about this. Are we all A-okay with the idea and logic here? Yeah?
Kind of the second half of what you said was like the 0.0005. Is that just a really low number, just that you get anything above that?
So what I'm doing, so the reason we're doing that, and maybe you missed the lecture or something, but when we compare floating point numbers for equivalency, computers really suck at representing decimals. So you might have two numbers that are seemingly... Were you here for the lecture when we talked about floating point issues?
Yeah.
Okay, so it's because I might say, like, 0.33, right? But what did that come up as? Like, I think 0.3 came up as like 0.2999999999999999999 or something crazy, right? So if I said, hey, is 0.3 equal to that value? Like, it's going to say no, right? Because they're not the same. So a way to address this is to say, well, if they were exactly equivalent, like imagine these were integers, and we didn't have to deal with floating point numbers. If their difference was equal to 0, that means that they're the same, right? Now in our case, we want it to be, well, the difference doesn't need to be 0, but it could be just very, 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 very small. Because if anything closer than 0.00005, good enough. We're fine. We found the approximation. I don't need to go anymore. So that's why we use that small value. If you're asking, like, well, is the fact that I did 0.00005 meaningful? Well, not beyond what I just explained. It was rather arbitrary. I could have done this and added another 0. Great. Right? And now if you're like, but why greater than, not less than? Well, we want to keep running the loop while the difference is bigger than that small amount. Some people might prefer this more, just logically how they think about it. Same thing, but maybe this just reads a little nicer to you. Well, it's not the case that the difference is less than a really small number. It's the same thing as, well, the difference is greater than, although I guess we've got that funny edge case of less than versus less than and equal to whatnot, but for our purposes, good enough. Did that answer your question?
Yeah, no, that's great. Thanks.
Awesome. Other questions? Yeah?
If you wanted to use this again, how would you get the last number out of the loop?
Well, new x currently has it. So there. So we just, like, it's because we stored in that variable last. And that variable still exists. It was defined up here, we're good to go. We don't have to worry about scope or anything, so we're happy. Other questions? I like answering questions. It's more interesting than just talking at you. No more questions?
But just a continuation. So if I want
in a new function, well, if we were writing a new function, like if we go down here, I would need to have the new function, def, that takes some value, I don't know, print, just a stupid little simple little function. If I want to then use that new, like I can just say ASD new, oops. And it's good to go. It's stored there. We can use it forever until we get rid of it. Other questions? Okay. How many people get this joke? Because year after year, less and less people get it. One person, two people. Not many. That's so sad to me. Because this is gold. Who is that guy? Al Gore. You know what's really bad is last year, and this isn't a joke. Last year when I did this, when we got to this slide, it was the day of the environment marches. And I mean, what's Al Gore famous for, other than being vice president? No. He's a really big supporter. This is sad. He's a really big supporter of like climate initiatives. Okay. Anyway, so that's why it was really bad that the people that were doing the climate march didn't know who he was, because he's, you know. Anyways, Al Gore. And what's he doing? He's doing rhythm? Well, kind of. He's dancing. So therefore, come on, that's funny. Yeah, there we go, see? Anyways. So we've heard the word algorithm before. Who here has heard this word a bunch and still going like, well, despite the fact that I've been programming for like a month, what the hell's an algorithm? Yeah. Well, an algorithm is just like the fancy word we use to describe the set of steps to do what you want. Like our programs are algorithms. This little function we wrote here, this right here is an algorithm that will do the approximation of cos x equals x cubed. It does. Algorithms, like any of the code you're writing is like algorithms, right? And if you're also wondering, like my girlfriend asked me, what's the difference between software and a program? Honestly, like it's the same thing. So algorithms are like half of computer science, okay? Let me take a step back. It's like half of programming. You know, all the code we're writing and these set of instructions that we're telling the computer to do, that is like half of the programming world. If not a lot more than that. But the other bit is data structures. Raise your hand if you've never heard the phrase data structures before. Yeah, a bunch of people. It's just a fancy way of saying somewhere to store data. Computer scientists are great at coming up with names for things. So it's some sort of structure we can define that will hold on to information for us. We learn in computer science in the first 1, 2, 3, 4 of like your 4 core classes that you're learning. We're going to be talking a lot about algorithms and data structures. How they work together. How your choice of data structure affects your algorithm and vice versa. How a choice of one data structure over another might be better in situation B, but not good in situation A or something. There's a lot of this going on. For a quick little activity, let's do this one together. Write down in English an algorithm for printing out the sum of all even numbers between 1 and n, where n is some arbitrary value, right? So, let's think. What would I tell a human who's got a piece of paper and a pencil? What would I tell them in order to give them enough instructions to do this? Okay, so here's what I'm thinking. Actually, you know what? I want you to take a minute and try this exercise really quickly with someone you're sitting closest to. And if you're not sitting closest to anyone, talk to yourself or something. Take a minute. The room should get a little loud. Let's see if you can kind of come to an idea. All right. I'm willing to bet, like, raise your hand if the person talking to you, yeah, I told you good enough that if you didn't know how to do this, you could do it, now that they've explained it. Wow, you all are really bad at communicating, I suppose. Maybe I spoke with too many negatives or something. So here's what I think. Here's what I think I would do. So I would tell someone, okay, here's the thing. I'm going to give you a number, an arbitrary number, n. Okay, and we'll talk about examples in a second. But I'm going to give you a number, n. It could be anything. And I want you to add up all the even numbers. Okay, so how do I explain that to someone who might not know? Okay, well, here's what we're going to do. We're going to keep track of the addition of all the values that are even. Okay, so, you know what, let's start at 1. You know what, we can even do this a little easier. What if we don't start at 1? What if we start at 0, or 2, it doesn't really matter. What if I start at, like, 0? Okay, so here's the, okay, I'm going to give you a number, and you're going to start at 0. Then what you're going to do is you're going to count by 2s. So what's 2 after 0? 2. What's 2 after 2? 4. So count by 2s. You can count. And every time you go to that next number that you counted by 2 by, you just add it to your, like, running total. Do you think, like, imagine you didn't know, like, what even numbers were or any of that. Like, did that explanation kind of make sense, Englishy, that someone can take and be like, yeah, I can do that? Of course it does, right? Like, because you're a human, you know what's going on, you can do that. Unfortunately, of course, we know computers aren't that great at listening, so we got to be really explicit. Now, you might find it difficult to go from that articulation in English, or whatever language, to Python, or whatever programming language you're talking about. And that's part of the art of programming. That's what you get a feel for. But there is this funny in-between language we like to use when programming. Or not even in programming, just when describing algorithms. We've got this funny little in-between language. Does anyone happen to know what we call this funny in-between language? Raise your hand if you think you know. One person, what do you think it is? Pseudocode? Bingo, it's pseudocode. It's code-ish. It looks like code, but it's not Python. It's perhaps a little more human-readable and more program-readable than, like, computer-readable versus human-readable than each other's. It's a little bit in between. So if we think about this in terms of pseudocode, let's see what we can come up with. And getting your pseudocode right, there's a lot of people who get really finicky about what's good pseudocode, what's bad pseudocode. I'm not too picky, but here's what I'm thinking. Okay, so we're going to start with, like, our running total. Okay, let's start our running total at 0 because we haven't seen anything yet, right? So I'm going to call that like RT, and we're going to assign that 0. RT is running total. You'll notice that I used an arrow for the assignment as opposed to equals. That's actually pretty typical in pseudocode because different programming languages have different syntax for assigning a value. Anyways. So maybe you know what? Okay, we're probably going to need a loop, right? And we're going to have a loop that has to count to n. So we're probably going to want some counter, right? Not mind-blowing. We want to keep track that we're keeping track of stuff. Like we're counting. Start counter, add 0. Oh, what did I just do? There. Okay, great. We've got counter and running total. Now, I can say something like while, maybe I'll write over here. While, do I say anything about up to and including? Between 1 and n. I guess I never really said, do I actually include n? What do you think? Should I go up to and including that number, or should I exclude that n? What do we think? There's no right answer, I didn't say.
Exclude.
You want to exclude? Okay, great. That's even easier. While counter c is less than n. Where n was, let's pretend, like if this is a function, n's given to us. N is n. Some arbitrary value. While c is less than this, all I need to do is make running total is going to be, I guess just, now this depends on how we program this. I'm going to program this the super lazy way. I'm going to say RT is going to take on whatever RT was plus the counter. And I'm just going to then update the counter is counter plus 2. I'm going to count by 2s. Start at 0 and then count by 2s. You might be saying, isn't it wasteful to start at 0? You could just start at 2. Yeah, you're right, I suppose. But that's just, I mean, this is a really simple example. And you might be looking at this and say, that's just Python, but you didn't use equals, you used arrows. Great, that's true for this particular case. But as our functions and code and algorithms get more and more complex, the pseudocode might look even more and more general. Anyways, this is kind of like this nice translation of English to code. I mean, it's mostly code. But let's turn it into actual code. So, delete. So, def, I don't know, sum to n. And then what do I say? Running total equals 0, counter equals 0, while c is less than n, colon, rt plus equals c, c plus equals 2, and then when we're done, print, nope, rt. Oh, I guess we should return rt. This is a function. And of course, that needs to be in the function. So we define it, and then, I don't know, let's do print sum to 5. 6. Well, does that make sense? 2 plus 4 plus, I mean, well, we don't include, yeah, that makes perfect sense. 2 plus 4, right? If you're confused, slow down. What does the code actually say? Sum to n, okay, we've got some n, start at 0. Is 0 less than 5 in this example? Of course it is. So we go inside that loop, rt equals rt plus equals is the same as that, plus whatever counter is. Counter is 0, so 0 plus 0 is of course 0. Kind of a waste of time, right? Then we add 2 to counter. So what does counter become? What's 0 plus 2? 2. Great. We go back up to the loop. Is 2 less than 5? Of course it is, true. So we go inside. Running total equals running total plus 2. Okay, great. So that makes running total 0 plus 2, 2. Then we go down to counter. Counter becomes 2 plus 2, that's 4. Cool. So we go back up to the top. Is 4 less than 5? Yeah. So we go in, running total equals running total, which was 2 plus 4. That gives us 6. Counter then becomes 6. Because we just added 2 to whatever counter was. Is 6 less than 5? No. We stop. Now, I was counting by 2. Here's a quick little quiz for you. How would I change this? Like, what would I change if I didn't do plus 2? What if I only counted by 1? Let's say I say to you, this is your big test, your final exam, here we go. Here's this code, you've got this, and it's supposed to sum up all the even numbers between 0 and 1 and n, exclusively. But here's the catch. You're not allowed to count by 2s, you got to count by 1. What could I do to make this still work? And we've seen this before. I'm curious if we know. I'll give you a minute to think. But we did see this before. We saw a solution to this problem. Raise your hand if you've got an idea. Really high, I want to see. Not many people. What do you think? Yeah. Exactly. You remember that, like, oh, we can say, like, if the number mod 2 is 0, that means it's evenly divisible by 2, which means it's even, like, by definition. So we could change it to do something like this. If C mod 2 equals 0, I know it's even. That's when I add something to RT. Now you might be wondering, oh, should that be there or there? There or there? You should never wonder, but you should think about it. Because as soon as you think about it, you'll have your answer. Do I only want to add to my counter when the number is even? If you just shook your head yes, reevaluate everything. No. We want to increase the counter when the number is even, but we also have to increase the counter when it's odd, because we're counting by ones. So regardless, we have to add 1 to our counter. Whether it was even or odd, we got to add 1. We only add to the running total when it's even. So only that bit is in the if statement. So here's one of those examples of, oh, I added the if, but where do I? This is a common area of confusion. What do I include there? What don't I include there? Slow it down. There's no silver bullet. You're not supposed to just know. You're supposed to go, do I want that in there? No, that doesn't make sense. So we run it. Let's see if we get the same answer. Should be 6. Yay, it worked. Any questions? All right. Oop. So, now we can talk about strings and a little bit about objects. Strings are special. They're a little different than the other primitive types we've seen so far. Did I ever talk about primitive type? Did I ever use that word yet? All right. It's a little different than the types we've seen so far. It's different than an int. It's different than a float. It's different than a Boolean. It's a little different. So, what's weird about strings? So first of all, I want to make a string. A equals hello world, print A. Did anything surprise you about this code? No. I could change this to an int. Nothing surprises you here, right? Also, another huge mistake people forget is you need the quotes around your literals, even if it's a single letter. You need those quotes. Anyways, we run this. This isn't surprising, but this might be. What happened? Look at this code. You may have never seen this before. Take 10 seconds. Look at this code and think what happened. I don't need to tell you what happened for you to figure it out. You can look at the result and reverse engineer what's going on. The first thing to remember is, what number do computer scientists like to start counting from? 0. We're weird. We start counting at 0. So 1 isn't the beginning, it's the thing after the beginning, weird. So raise your hand if you look at this and go like, yeah, okay, I clearly know what happened. I mean, raise your hand high, I want to see, because if your hand's not, I'm a little concerned. Okay, so, what happened? Like, you don't know what happened? Yeah. No, you don't? So what about this is throwing you off? The 1. So what did you see happen here? Like, what did you expect to happen? Sorry, I can't hear you. Maybe take this down. So it gave me a letter, right? But, I mean, you said the 1's throwing you off. What letter would you have expected? A? Okay, interesting. Remember, A is the string, hello world. Hello, comma, space, world, exclamation point. And computer scientists like to start counting at 0. What that means is, give me a single letter from the position, whatever's in the brackets, the square brackets. I put in 1. If I put in 0, what would we expect to see? On the count of 3, yell it. 1, 2, 3. H. Because we start counting at 0. If I put in 2, on the count of 3. 1, 2, 3. What if I put in 3? What if I put in 10? I guess I get that guy. What if I put in like 101? Well, index error because there is no letter at location 101. There's only 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I say 12, we get that. 13, no good. We're out of letters. You know what's cool? Oops, still angry because 13. Let's make that 10. I asked, what's the length of A? And it told me how many letters there were. Isn't that cool? Now, put your hand up if you're like, wait a minute, we just tried to get the 13th letter and it yelled at you. Raise your hand if you see that as a problem. Why is it not a problem, though? Let me put it this way. We start counting at 0. Watch how many times, I'll just do it with like a tally on the board. How many ticks do I have if we start counting at 0? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many ticks are there? 13. We got to make sure we're counting 0. If we start counting at 1, I would have only drawn 12 ticks. So, the last index because of zero-based indexing, the last index of a string, the last letter, will always be length minus 1. Here's something cool. I can even do this. Len of A minus 1. And no matter what this is, I'll always get that exclamation point. Because what it'll do is it said, okay, well, it's 57, and then we want the thing on location 56. Isn't that cool? Anyways, we'll wrap up here for now.